Okay, we are back to building a computer in Turing complete. So we finished basic logic, and now we're in trying to do these arithmetic and memory lanes. Maybe I should go down the arithmetic path first. We'll see how it goes. All right. Double trouble, what is that? Because we are so technologically advanced, we have machines fold our socks. Unfortunately, the circuit that detects the sock pairs broke on the machine. All right, this level has 4 outputs. Output green when 2 or more of them are green. Don't overthink this level. It's probably really simple. Gosh, I kind of want to think of, because it told me not to overthink it, I kind of want to do something simple. The easy way is, again, like I usually do, just go through each one, look at only where they're green, and combine them together with OR gates. So we're going to say and actually, even just looking at it like this, I think maybe we can simplify it. Or this one and this one. Hopefully I didn't screw that up somehow. Looks like I might have somehow screwed this up. Alright, hold on. These two. And then a bunch of ORs. I guess we can simplify this with some triple ORs. Yep, so if only one is on, should be green, otherwise, yeah, should be red. Okay, that works. Yeah, just ANDing them all together. Let's test it. Yay! Odd number of signals. Using a maximum of 3 components, only output green when an odd number of inputs are green. Now we can only use 3 components. That's going to make this kind of hard. So that was a hint. Let's not use the hint. Okay, now my first instinct, well, if we were going to do this the way I would normally do it, right, I would just AND all the ones together that are green, right? Do an AND for each one and then OR them together is what I mean, I guess. So we do, say, like a double AND for each one, right? And this first one is green, and then we would invert, and then we would invert this one. Oh, I can't just put an inverter there. All right, I have to connect it. Invert that one, and then I do the same things like that. And that's this one working, right? Oh, I would have to put an OR there, and then hook that OR up. That would be and that would cover this one, and then I have to do one for each one where they're green, because this only works for this exact input. It doesn't work for anything else. That would take me way too many gates. And I've done something here to screw it up anyway, so... Oh, that's it. It should be an AND. That's why. It should be an AND. That's why it looks screwed up. All right. But anyway, that would be way too many gates. That'd be what? 1, 2, 3, 4, 5, 6. 6 times 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that'd be like way too many gates. That's not going to work. My next instinct would be to use these triples, like the triple OR, the triple AND, but I don't think that really gets us anywhere. If you were to like try to chain these together somehow, like this would just tell me if any of them were on, which isn't really that useful. And then if I did the same thing with AND, it would just only tell me if all of them were on. I think the only thing that'll work is either XNOR or XOR. I think it's got to be XOR, right? Because this will tell me if 1 is on in each one. Oh, that's a NOR. Gotta select the right one. This will tell me if 1 is on in each one. But it'll be off if both are on. So it'll tell me if I have even or odd, right? And then so if this one's on, that's 1. this one's on, and then if they're all on, I want something that'll give me no, which I think is just another XOR, right? So that'll work. Yeah, so if they're all on, if it's 3, it's off. If it's 2, it's off. If it's 1, it's on. That's pretty simple. Yay! Alright, let's skip, I guess we're skipping memory stuff for now. So let's go to counting signals. Okay. The output component of this level is binary counter, where the first 3 pins correspond to 1, 2, and 4. Use the binary counter to display the number of signals. The solution to this level is not very neat and requires more components. All right, we're gonna need a lot. So I think, like, what if we hook this up? It's 1. If we hook the second one up, it's 2. The other one up, it's 4. Okay, so we're gonna, I guess, try to do each one individually. Like, we'll start with the 1s, then we'll do the 2s, and then we'll do the 3 or the 4. Right? So we'll do this input first and this input. Let's start with the 4th, because that should be the easiest one. We just need to AND them together. Oh, wrong one. AND them together. Right? And then AND those together. And then put that there. So this will only trigger. Oh, I did not hook it up. There we go. So this should, I did not hook that up. This should only trigger when all 4 are on, right? So this gives me this one covered. I'm gonna do the same thing with the other ones. Those should be OR together. Okay, now we got 1 and 4 working. Right, we got 1 and 4 working. Now I got to do 2. Okay, I don't even know where I'm going to put this because I don't have room. Okay, so I gotta get 3 working, but I think I'd probably find a way to just cannibalize some of these bits. Okay, what we have here is an utter abomination of the most spaghetti code. There is definitely better ways to do this, but I did not do it those better ways. I did it the worst way possible. But who cares? It's not pretty, but it works. Let's check it out. Let's test it out. Oh my god, that is terrible, but it works. Okay, continuing up the arithmetic path, let's do the half adder. We measure the universe with numbers, so your machine must learn to count. Alright, so now we have to deal with 2 desired outputs, a desired sum and desired carry. So let's just look at this sum first. If it's 1 and or the other, then it should be 1. Is that the same as... that looks like the same as the XOR. Correct, right? Yeah, that's the same as the XOR. So we can hook that up just sum up to just an XOR, I think. Looks like on the screen here it's not turning green, but over here it is. So I think that must just be a bug. But yeah, so the sum we got working just with a basic XOR. And the carry is all zeros unless it's both of them, which is an AND, right? Yep, so that's the same as an AND. That should be simple. Right? Let's check that. Yeah, easy. Double the number. Let's do the full adder since we just did the half adder. On the previous level, we added together 2 inputs. This time we add 3. Once again, the inputs together in binary such that the result is either 0 or 1. Okay. Okay, so this is the same thing as the last one, except we also have a third carry input, a potential carry. So we have to worry about 3 inputs now, which makes it obviously a bit more complicated. But we can take them one at a time if we want. So there we go. Again, we have this bug, it looks like, where that's not turning green, but it's turning green over here. So I think that's working as intended. Yeah, it looks like it's working as intended. Okay, now we got to worry about the carry. It looks like we can switch the wire color. I guess let's do orange for the carry. Why not? All right, so this looks like spaghetti, but I believe we have it all working properly. Yep. Double the number. Let's see what this is about. The input and output of this level are using bytes instead of bits. One of the 2 new components you are given takes a byte and splits it into bits, and the other does the opposite. Using those components, figure out how to double the input up to number 127. Okay, so we have different components, bit splitter and a bit maker. So this should, I guess, take the bits apart. Oh, yeah, okay. And this puts them back together. So I mean, we're gonna have to do it like that. And if we're just doubling the number, right, we can hook up 1 to 2, and 2 to 4, 4 to 8. 8 to 16, 16, 32, 32, 64, 64 to 128, and that's, I think, as far as we got to go, because, well, we can't anymore. Right? That's all we have to do. Yeah, okay. That was easier than I expected. All right, what is next? Byte or byte not? You may think it is unethical to eat all the earthlings that don't win the competition, but actually it is okay because you lived good lives in the wild, and we don't let good meat go to waste. All right, fair enough. Or each bit of the input and output the results. Oh, we can use them all. I mean, this should be easy if we're just ORing each input together. I mean, this is going to look really messy. I can spread these out a bit. But then we just need to basically go like that, but we got to do that for every single one. So that's a lot of ORs. Okay, so I think that's all this wants. Byte or, we're just ORing each bit of the byte. I'm pretty sure this is what I'm supposed to be doing. Yep. Byte not. Our previous model of brain size being the main predictor of intelligence was naive. Tool making and usage is key in the early evolutionary stages of developing intelligence. Therefore, the number of arms on a creature clearly the main predictor of intelligence. Well, it looks like this guy has 2 arms, but I guess we don't know what's going on underneath. Okay, not each bit of the byte input. This is basically the same thing we just did, except we're just going to do a not for each one. And that is exactly, I think, what we need. Onwards. Okay, it looks like we need to dip into memory in order to continue on towards the arithmetic part. What is this? A bit switch. What is this? If the components output different values on the same wire, you get an error. However, some components have gray output pins. These are not outputting at all when the component is not enabled. This is the case for the bit switch component. When the top pin is red, so I guess this one, when that's disabled, or sorry, when this is red, the output is disabled. This means that more than one of these gray output pins can connect to the same wire and not cause an error as long as they are only one of them is enabled at a time. Use 2 NOT gates and 2 switches to build an XOR gate. Okay, so I got 2 of these and 2 of these. Okay, I think I kind of understand how this works. It's a little bit harder to think about. But I guess I need to hook one of these up into another one? Am I crazy? Okay, so I think I kind of get it. So it took me a little bit. It's taken me a little bit to kind of figure this out because I'm kind of not really understanding exactly how this works. But I think if this one is enabled, right, then we want to make sure it disables this one. And then vice versa. Yeah, so this is getting the input from the first one, but if the second one is off, then it will get enabled. Same thing with the other one. This is getting input from the second one here, but if this one is on, then it's going to switch off. And that gives us our copy of the XOR gate. That was very confusing for me. For whatever reason, the way this is set up is kind of confusing to me anyway. But this should work, right? Alright, adding bytes. Hopefully this one's a little simpler. I think anything in the memory section is going to screw me up, but I think arithmetic is going to be okay. If the result does not fit in 8 bits, turn the output carry green. You can think of it as a 9th bit. Finally, okay, I feel like we're going to need a lot of space for this. So let me just move these out. So do we have our adder? Yeah, we do have our full adder that we can access. And we're gonna need it for every single byte. So we're gonna have to break this out, right? And then same thing with this one. And then we're literally just gonna have to add. So like this one, we had these first ones. Oh gosh, yeah, I'm gonna need a lot more room for this. So the first carry goes into the first bit. And we're gonna need to just copy this exact pattern for the rest of them. So then we just gotta like daisy chain these together. So the carry bit for each one is gonna go in like that. All right, and then we can just put them all back together right here. There we go. Yep, that looks like it should be working. Negative numbers. Oh, exciting stuff. To know the difference between things, you need to know subtraction. To get subtraction, you first need to get negative numbers. Yeah, so I always thought that with making binary numbers negative, you literally just have like a flag where the first one, if it's 1, then it's negative. That's actually not the case. It's really like turning this most significant bit, they call it, the one that's over here, negative, and then kind of adding them up, the rest of them up like normal. Why do you do that? I think it just makes a little bit easier sense. Like when you're actually put things together, it's a little bit easier to make it like that, to make a circuit like that, than it is to just do it where this is a flag. I think it also, if you have this as a flag, there's something like you get 0 and -0, which is just, I guess, not efficient. But this looks like the same game as before. We just have to remember that this is negative. That was not fun. That was hard. That was hard to think of -128, like subtract on the fly. I did not like that very much. It gives you like a good idea of how negative numbers work in binary, or how they usually work in binary. But man, it is hard to like think about it like that. At least for me, it's really hard to think about it like that. It's not like a hard concept to learn, but man, it's hard to do it on the fly. Signed negator. Taking the input as signed, where the eighth bit is -28, making a component that takes a number and negates it. For example, 4 negated would become -4, and -9 would become 9. For this level, you probably want to turn on signed numbers, so the highest bit is -128. Click the +255 located in the top panel. Okay, so we want to toggle the number format. Invert the sign of the number. There's actually like a trick, and I have no idea how you know this. I don't know how you know this without like knowing this system, but what you really need to do is you negate everything and add 1. So here we've negated everything, but the problem is we need to add 1. So I think what we can do here is probably negate everything except the first bit. Let's try that. No, that does not work. So like we're close, right? So we got 8 and we got -9. So how would we add 1 with what we've got here? I guess we need an adder. So we want to always add 1. I think we can use this. But instead of this, we'll just do the carry. We'll do the carry on. And That would be this one. I guess it doesn't matter, does it? Yeah, there we go. That somehow works. That makes sense. So yeah, we are just adding 1 here. All right, let's try it. I don't know how you'd figure this out without first knowing the trick is negating everything and adding 1. But yeah, there you go. That's how you make a positive number and turn it negative in binary. All right, it looks like there's not that much left in arithmetic, but we are now stuck. We are going to have to start going down the memory side. So I guess we'll stop there and we'll do memory next time. And then we can finish up arithmetic. And then we can actually move on to CPU architecture after we have all that stuff done. All right, thanks for watching.